continuing from where we left off before the test, before the electrostatics test. We will go through the electrostatics test one day as well, I hope. That's the plan. We gave you this analogy. We said you could think of a circuit as a ski hill where the voltage source was like a chairlift. A chairlift lifts you higher, raising your potential energy, gravitational potential energy. A voltage source raises the electric potential energy of a charge. And in the same way that when you're on a ski hill, the only way that you can get to the bottom of the ski hill is to lose all your height. To go through a circuit, when you get to the bottom of the circuit, which is the bottom of the battery, you must have lost all your voltage. If you have not lost all your voltage, that's impossible. You've messed up. So we said voltage was like height. We said that current was like the number of skiers. More popular means bigger current. And we did say that even though electrons move from negative to positive, here's our symbol of a battery, electrons flow from negative to positive. We said it's so much nicer to think about stuff flowing downhill. This is my rant about how Ben Franklin got the charges wrong. He should have called protons negative, and he should have called electrons positive. It would have been much nicer. Even think about in Science 9, when you're always having to think, I've lost an electron. I'm positive, not negative, because lost usually means you should be down something, but no, you've gained a charge. He got him wrong. So we've said conventional current is defined as which way the protons would move if they could. And you know what? An electron moving to the left is mathematically the same as a proton moving to the right anyways. Every circuit offers some resistance to a flow of charge. The circuit symbol for a resistor is a series of short-angled lines, which you should recognize from Science 9. This resistance is really due to electric friction, where electrons collide with the atoms in the material that they are passing through, and these collisions cause them to lose energy. Typically in the form of heat, but we're pretty clever. We can do an awful lot with that. This energy lost by the electrons heats up the material. A loss of energy implies a loss of voltage. In a resistor, you always have a voltage drop. You lose height. You know what? A resistor is like a ski hill. The battery is like the chairlift. You gain energy, you gain voltage, and then you go through the resistors, losing height, losing energy, to get back to the bottom of the chairlift. So current typically moves from a higher voltage to a lower voltage, or James, skiers ski downhill, not uphill. And that's why we've decided to focus on the positive charges, Liam, even though technically they don't move. It's so much nicer to think that way. The amount of flow through the circuit depends on the resistance and on the voltage. So you ready? What can be said about the current flow, the number of skiers in each case? Fill in either large current flow or small current flow. Suppose you have a high resistance. Now, another way to think about resistance is the width of a hallway. High resistance means really narrow hallway. Could we get a lot of students through that hallway, or a smaller number of students through that hallway if the hallway was really skinny and narrow? So high current, lower current, low current. And remember, the symbol for current is capital I. What if you have a low resistance? What if you have a really, really wide hallway? What if you had a large voltage drop? So now let's go back to my ski hill analogy. What if you had a really big hill? Is that more popular or less popular? What about the bunny hill, a small voltage drop? Okay. If I wanted to write an equation, it looks like as R gets big, current gets small. That must mean R is on the bottom, because when that number gets bigger, your answer gets smaller. It looks like when voltage gets big, current gets big. That means the V must be on the top. This is the equation for current, although you wrote it in Science 9 as V equals I times R. This is Ohm's law. You don't need to memorize it. You will memorize it because you'll be using this 90% of the time. V equals I times R. That also means that I equals V over R, and it means that R equals V over I. Right? Okay. Voltage drop across the device or across the resistor or across whatever situation we're looking at. V. I is the current. How many amps are flowing through it? We said current was the number of charges per second. It's how many skiers are flowing through it in our ski hill analogy. R, the resistance. We're talking about resistance. By the way, technically, to be consistent with the previous unit, I really should write delta V for voltage change or voltage drop, and Ohm's law should really be delta V equals I times R, but as you may have noticed before, this notation is cumbersome, much like time is always a delta, and so the delta is dropped. So when you see the V, you should think it's a change in voltage or a voltage drop when we're talking about circuits. The units for resistance are ohms. Symbol for ohms is a mouse hole in a wall. Yes, it's a Greek letter omega. 1 ohm of resistance means that if you have 1 volt and you drop 1 volt going through that resistor, 1 amp will be required to pull that off. Good conductors have low resistance. Poor conductors have large resistance, high resistance. So I have here mix and match some typical resistances. I have 6 different items on the left, and I have 6 different resistances on the right. They're scrambled. Look at the ones on the left. Which of those do you think would have the highest resistance? Which of those is the worst conductor? No. Which is the best insulator, the worst conductor? What do we use as an insulator when we're designing? What? Glass. Glass has nearly an infinite resistance. Now, I mean, if you pump enough current, you can get stuff to go through glass too, but of the remaining 6, which one of those would have the lowest resistance? Which one of those is the best conductor? Copper wire, it's why we use it. On the right-hand side, which is the smallest resistance that's left? 0.1 ohms. See, because we're going to go figure out how we're doing this. We're going to kind of go process of elimination. Okay? Of the 4 that are remaining, I'm going to tell you the worst conductor remaining, the highest resistance remaining, human skin. We're not that good a conductor. Our skin. Inside, we're pretty good conductors because we're mostly salty water, but our skin itself is a pretty good conductor. So what's the average resistance of human skin? Look at what's left and pick. 100,000 ohms? The next best conductor is the object that heats up the least. It's the electric motor. Electric motors get a little bit of heat, but not much. You can imagine a kitchen fan, you can let it run for hours and hours. If you touch it, the motor will only be a tiny bit warm. So that's going to have the next lowest resistor. And I'm not going to assess you on this. This is, again, anytime I show you something new, I like to try and give you an idea of what's really big and really small. For what it's worth, light bulb typically has around 200 ohms, and a typical lab resistor is around 2200 ohms because we want to keep the current small enough that you don't kill yourself. Safety first. Yeah?
Is that like an incandescent bulb, or is that like a...
That would be an incandescent, yeah. LEDs and the CFC, totally different. Good point. We're going to be in our magic physics world. Wires, when they heat up, their resistance changes. We're going to pretend that that doesn't happen. So our changes with changes in temperature or the amount of current, we're going to ignore that, and it's not too big. Oh, and our actual wires won't have any resistance. We're only going to look at what they're connected to in our magic physics world. Skin is a pretty good insulator. typically tens of thousands or even hundreds of thousands of ohms. But it'll only protect us up to a certain point. Once the voltage exceeds a certain value, the skin will break down. It'll ionize the same way air could ionize from lightning. And on the inside, we're basically salty water. And this conducts electricity pretty well. Once beyond the skin, the danger to electrocution lies in two effects. First, there's a heating up of tissue as electricity flows. This can cause severe burns and destroy internal tissues and organs. Secondly, the flow of electricity through the body can disrupt the body's own electrical nerve impulses, leading to temporary freezing or paralysis of the muscles. And when these muscles in question are your heart and your lungs and your diaphragm, that's not good. Once beyond the skin, the heating effect grows larger with larger currents. So in the US, I think they still use the electric chair horribly to execute people. They're putting a pretty massive current through that individual. But the current required to cause your heart to fibrillate or to make it difficult for your diaphragm to expand and breathe is really small. It's about 100 milliamps. It's about 0.1 amp, which is not big at all. So be careful when dealing with electricity. I've told you that your skin is a pretty good insulator. I'll prove it. I got a new physics toy. You guys are the first ones to see it. Next page. So, in our ski hill analogy, resistors act like ski slopes that connect the top of the hill to the bottom. And the amount of resistance or electric friction, you know what? It's sort of like the depth of snow. When snow gets deeper, now this is where my analogy breaks down. I know deep powder is popular, but when snow gets deeper, we're going to say you can't get as many skiers on the ski hill because they can't go as fast. The snow is so deep. When resistance goes up, when the snow gets deeper, the current goes down. Low resistance is hard packed snow. You can get lots of skiers down that hill really fast. So Ohm's law for ski hills states that the flow of skiers varies directly with the height of the mountain and inversely with the depth of the snow. You know what? It says this: the flow of skiers depends directly on the height of the mountain and inversely or reciprocally as the depth of snow. That's V equals I times R. Okay. Example 7, find the current in each case. Say, what? So, here is our first ski run. This is eventually going to seem babyish to you and easy. We're going to go skiing together. We always start out at the battery if you know it. What's the voltage of this battery, Rob? So I'm going to ask you the same question. I'm just going to phrase it differently. How high is my ski hill? Same answer. Now it's 6 volts, but that's how high we are. Look up, look up. First thing we're going to do is we're going to draw arrows showing the current. The current goes from the positive. Do that, draw that to the negative. Takes 1 second, and you've just decided which way you're going to ski, which way you're going to move your eyes. Robbie, how high is the chairlift? 6. So I have to lose 6 volts when I get back down to the bottom. Okay? Well, there's only one hill. How many volts must I lose going down this hill? 6. Yep. All of us right now, let's label this hill, this resistor, with 6 volts. Robbie, how many volts do I lose going through this resistor? How many volts must I lose going through this resistor? What's the resistor? How big? 25 ohms. And I just said we had V equals I times R. I equals V over R. How many amps are going to flow through this circuit? What was the voltage in that resistor, Robbie? 6. What was the resistor? 25. How many amps? Go ahead. 6 over 24 would be 0.25, so it's going to be a little less than 0.25. What is it, like 0.23? What is it? 0.24? Amps. You okay with that? Now that there is a good circuit. It is a safe circuit. It's a well-designed circuit. This next one here, you'll notice has no resistor, which means the wire has to behave like the resistor. This is a short circuit. How many volts are we starting out with, Robbie? 6. So we must lose 6 volts, but this time the only place to lose it is by heating up the wire. This is bad because now the current is going to be 6 divided by 0.001. How many amps?
Yeah.
6,000. Not good. That will do one of two things. That will either drain your battery very, very quick because those charges per second, current is charges per second, are coming out of the battery. It'll burn that battery really, really quick. But probably it would heat up those wires red hot. And red hot wires in a house circuit, fire bad. Okay? That's a short circuit. So, oh yeah, I knew I would have written something down. The second diagram is an example of what is known as a short circuit. It's called short because it has basically zero resistance or almost no resistance, which means you get an almost infinite current. You get a huge current, and current is what's generating heat. This depends, of course, on the voltage source. If that 6 volts was a little AA battery, a couple of AA batteries hooked up in series, you're probably okay. But if it was a voltage source that had unlimited charge, if it was somehow hooked up to the power grid, you're going to cause a fire. Okay? So if you short circuit a AA cell using lab wires, all that's going to happen, you're going to burn out that battery in about 5 minutes. If you short circuit a car battery using lab wires, the battery has enough charge to make the wires very hot, maybe even melt them. If you short circuit BC hydro, fire is bad. No, that's why we put fuses and circuit breakers into our system. They're designed to trip and cut the circuit off whenever they detect this happening. We'll talk about how that works a bit later. Okay? So as we'll see in the next lesson, large currents means that wires will get hot and melt, possibly creating an electrical fire. You have to take off? Okay, you might be getting lesson 2. We'll see if I get that far. I'm also going to ask you about using electric meters and how you use them properly. I'll give you pictures on a test and say which of these have them set up in the correct place. The 2 main meters we're going to look at are voltmeters. What do you think voltmeters measure? Voltage. And then amp meters. What do you think amp meters measure? Except they don't call them amp meters. Over the years we dropped the P, we just call them ammeters. They measure amperage. Okay? So, current and voltage are measured using ammeters and voltmeters, respectively. Consider the following circuit. So the real circuit, we've hooked a light bulb up to a 12-volt battery. Our circuit drawing, we have a 12-volt, 6-volt battery. We have a 6-volt voltage source and a resistor. Here's our light bulb. To properly measure current, remember, that's the number of skiers. The only way that you could count the number of skiers in a mountain is to make them all go through the same gate while you count them. You can't give them a different pathway that they can get past you and you didn't see them. So to properly measure current, the ammeter should be connected so that all of the current in the circuit runs through it. We need to actually physically break the circuit and insert the ammeter in series. We'll be talking more about series and parallel later on in the unit, so that all of the current, which the current would go this way, would go this way, would go this way, you'll notice all of the current has to pass through it. If you set it up like this would be incorrect because you could have current going through here and you have no way of measuring it because only a few skiers would go this way. In fact, very few skiers would go that way. No ski run, no attractiveness. So to measure current, you have to physically splice the ammeter into the actual circuit in series. That's a lie. There are now ways to do that by detecting changing magnetic fields, but for now, we'll do the old analog system. What about for a voltmeter? Well, I said voltage was like height. To measure the height of something, you have to measure something in 2 locations, the bottom and the top. You can't just, for example, if you're trying to measure how tall something is, just put one mark on there. You have to know where you're measuring from, where the bottom is. Usually we measure from the ground. In a circuit, you can measure from anywhere you want. But to measure voltage, you have to set up the voltmeter in parallel and you have to connect it in 2 locations and measure the change in voltage, the height difference between those 2 locations. So this would be correct. This would be incorrect. This would only tell you what was going on right there. It doesn't tell you how high you are compared to where the ground is. Technical comment, we focused our introduction on direct current. Direct current, DC is the abbreviation, always flows in the same direction as a constant value. Everything that I'm teaching you pretty much can also be applied to AC, to alternating current. Alternating current has a magnitude that varies as a sine function. The voltage goes this way, the voltage goes that way. The voltage goes this way, the voltage goes that way. The voltage goes this way, the voltage goes that way. It has a frequency of 60 hertz. So it has a period of 1 over 60, has an amplitude of 120. I think the amplitude's the voltage. Can't remember now, I'd have to go look it up. What comes out of your plugs is actually, I typed 110 volts. It's actually 113.4 volts, I think. We use 120 for simplicity because it makes the math nice, and you're not going to be off by that much. So you'll always talk about, in North America, we have a 120 volt system. In Europe, they have a 220 volt system, which is why you need the adapters when you go to Europe. What's your homework, part 1? You can do number 1, you can do number 2. Number 5. Number 6. And then I'm going to move on to lesson 2 today. So it's a little weird, but lesson 2. Oh, got my resistance comic. Join the resistance. Okay. Joule's law. These are the big 2 equations. There is a third one that we'll get to in about 5 lessons, but this is how you can calculate voltage, current, resistance, and now we're going to talk about power in watts, electric power in watts. And what you're going to hear me say is, if you know any 2, you can find all 4. If you know any 2 of them, you can find all 4. Electrical power. Recall, as charges flow through a circuit device like a resistor or a light bulb, they lose energy due to collisions with the atoms of the wire. You go from a higher voltage to a lower voltage. So as an example, supposing you were sitting at 8 volts right here, and you end up at 3 volts right here, how many volts did you lose going through the resistor? Do the math. 5. Now, typically what we will do is we will only label the resistor, and we won't label the left side or the right side. We'll just say, oh, but that's how you figure out how many volts you lost. How many volts did I have coming in? How many volts do I have going out? Well, that's how much I lost. I'll label the resistor with that. Remember, voltage is energy per coulomb. It's joules of energy per coulomb. So if you lost 5 volts, you've lost some energy going through that resistor. It's transformed into heat or other clever things. This energy lost by charges is related to voltage drop, since potential energy is QV. So we can now find an expression for the rate at which charges lose energy. The rate at which energy is changed, that's what we call power. Power was how fast work was being done. Energy was the ability to do work. But we can't go work over time. We want to come up with a power equation that has voltage and current and resistance in it. But you all know power is measured in watts, and you know light bulbs and appliances all have a wattage on them. That's telling you how many joules of energy per second they're taking. So power is energy loss over time. Power is going to be QV over T. Power equals, I'm going to move the V to the front, and I'm going to group the Q and the T together. I made it a big Q just because. Hey, what's Q over T? Check your formula sheet from this unit. Current. This is Joule's law. Power in a circuit is the voltage at that location, or the voltage lost at that location, times the current going through that location. That's how many watts of power is required. Typically, I'm more interested if I'm at home in knowing how many amps my appliance needs. I know the voltage coming out is 120. I look up the wattage on the back and I can say, okay, how many amps does it need? Most of your household circuits can only handle 15 amps. As soon as you have more, the breaker will trip. So if you're ever wondering why your breaker is tripping, it's because, trust me, if you add up the number of amps that each of these appliances from this outlet need, it's bigger than 15. Power is, another way to think about it, the energy drop per coulomb of charge times the coulombs of charge per second. Why did I write it that way? B. I'm good with this. Power equals VI. This is electric power. Power is still work over time, but it turns out another way to write a watt is a volt amp. Muck around with the units, trust me, you'll eventually find that stuff cancels and you end up with joules per second. There's two other versions of Joule's law. So this is the only one that's on your formula sheet. It's VI is on your formula sheet, right? Is the one? Yeah. Oddly, this is not the one that I use the most, only because typically, if I'm looking at a specific situation, voltage is the thing that I don't know. It's often the thing that I'm trying to calculate. However, V equals I times R. So that's going to give me two more expressions. I can go power equals I times R times I. Because V equals I times R, so I replace the V with the I times R. So it's I, R, I, except how would you write I times I? What's a better way to write that? This is actually the one that I end up using the most. It's not on your formula sheet. This is the one that I end up memorizing during this unit. And again, only because I'm lazy, and as I'm doing the questions, most of the time I know the current and I know the resistance. And I want to figure out how many volts I'm losing going through that resistor. Oh, also, I equals V over R. I got the I by itself from Ohm's law. So that means that power equals V over R. There's power equals VI. Except, what's a better way to write V times V? Here is the third version of Joule's law. Having said that, both of those that I've written are redundant. You can survive Joule fine without them if you know V equals I times R and P equals V times I, and they're both on your formula sheet. That second one, the I squared R, might save you one line. We're finding energy lost by the charges. We're finding the work done by the charges. I should really use the work energy theorem, the idea that work is the change in potential plus the change in kinetic. However, once you flip the circuit on, all the charges are moving at a constant speed. If you're moving at a constant speed, what's your change in kinetic energy? And that's why I was able to go to QV and just use that. There is a slight increase right when you flick the switch on. It does use a tiny bit more energy. That's why you may have noticed for really big appliances, right when you flick it on, everything dims for a little second and then comes back up. Okay? That's because there was a change in kinetic energy, and that energy had to come from somewhere. We're going to ignore that, Simone, because that's yucky math. Okay? So that's why I can just say QV, and then that's how I was able to end up with power equals VI. So let's apply this to a circuit. We're going to apply this to a household circuit. This is an AC circuit. The symbol for a direct voltage source, don't write this down, I told you was a short line and a long line. The symbol for an alternating voltage voltage source is a circle with a little sine wave through it like that. So here's the symbol for alternating current. But the physics that I've taught you will still work. It says, find the current in your house wires if you plug in a 1400 watt hairdryer. So right here, we are using 1400 watts of power. And I know that my voltage is 120 volts. And they want me to find current. Okay. Power equals VI. Nick, how would I get the current by itself? So the amount of current that is going to be used by this hairdryer is the power divided by the voltage. It's going to be 1400 divided by 120, which is what? What do you get? 11.7 amps? Your household circuits are designed to handle 15 amps. Any more than that, and now you have so many skiers, so many charges moving through there that the electric friction is dangerous and can start to heat up the wires. If you have more than 15 amps, the breaker will blow. So here's my first question. Could you run 2 hair dryers from that plug? No. It would require 23.4 amps. You may have found that. I don't know how your houses are wired up, but there's one plug in my house where I live. I rent a suite, and the people upstairs, we must be on the same circuit, and they must have a pretty big appliance plugged in there because it's in my kitchen. It would be the most convenient place for me to plug in my microwave. I can't plug in my microwave there. I blow the breaker every time. So they've got something up there running. I don't know what. Objects that move more heat around use more power. So we did our mix and match with resistors. We're going to do our mix and match with appliances. Over on the left, I have, I think, 7 different appliances. On the right, I have 7 approximate power usages, but they're scrambled. Look at those appliances. Which one of those moves the most heat around? And your hint is it moves so much heat around that it needs a special plug. It can't run off 15 amps and 120 volts. It has a special plug. Duncan. Clothes dryer. If you pull your dryer off of the wall, there are 2 items in your house that have special plugs. Your clothes dryer and your stove, unless your stove is a gas stove. But if you pull them off, you'll see it's a big, thick outlet. It's a really different looking outlet. So the clothes dryer is going to use the highest wattage. What's the highest wattage over on the right-hand side? 48. Hey, I can do another one. Average incandescent light bulb. What's the wattage on an average bulb that you put into an outlet? 60 watts. I can fill that one in, because I've changed light bulbs before. From what's remaining, what do you think moves the most heat around? What do you think would have the largest wattage? Hot water heater. Now, mine is a gas one. I don't know if electric hot water heaters have a special outlet. I don't think you would need to, because you can gradually heat up the hot water. But yeah, the hot water heater is going to be the 3200 watts. Anybody know the wattage on a large microwave? Well, you know what? Actually, which of these uses the least amount of power? And your hint is a tiny little AAA or AA battery can have it run for about a year. My little wall clock behind me. That uses about 0.1 watts. Of the 3 that are left, which one do you think uses the most power, the most wattage, moves the most heat around? Okay, Okay, it's large microwave. Large microwave will typically be 1100 or 1200 watts. If you have a small microwave, that'll typically be 800 watts. That's why, by the way, whenever you nuke something, when you read the instructions, it always says microwave oven times may vary, because they don't know what wattage you have in your oven. Okay. Kitchen fan. Yeah, they don't throw off much heat. Computer, about 800 watts. Okay. If you wanted to, you could figure out how many amps each of these use if they're plugged into a standard 120 volt outlet. Yeah. What about an electric car? I don't know. I'd have to look that up and do some crunching. Patience. I have a video, but later in about 4 days, I think.
You test drive a Tesla?
I took a Tesla for a test drive a couple summers ago. It's unicorns and rainbow dust. It's wonderful. Yeah. Electrical energy. So energy is measured in joules. How can we get electrical energy? Well, power is energy or work divided by time. So that means if you want to know how many joules of energy an electric device is using, it's going to be the power in watts times how long you leave it on for in seconds. And this is how they calculate your energy bill, your parents' hydro bill. Except a joule is such a small unit of electrical energy, it's common to use a larger unit, the kilowatt hour. Kilowatt, power, hour, time, but much larger numbers, because if they didn't do that, your parents would be receiving bills in the tens or hundreds of millions of joules, and they would freak out. As opposed to the kilowatt hour, where you get, 63 kilowatt hours. That's a number I can wrap my brain around. Oh, last month we used 61 kilowatt hours. We saved some electricity. You can wrap your brain around that. 1 kilowatt hour is 1,000 watts times 3,600 seconds. 1 kilowatt hour is 3.6 times 10 to the 6th joules. A typical household uses about 1,000 to 3,000 kilowatt hours of electrical energy a month. And this brings us to a sort of happy problem, but a problem nonetheless. Suppose you took a 60-watt light bulb, your standard bulb, and you left it on for an entire month without turning it off. We'll say the month has 30 days, 24 hours a day. First of all, how much energy will that use? Okay. I know power is energy or work over time, so energy is going to be power times time. James, how many watts of power is this bulb using? 60. Yep. And then the time is going to be 30 days times 24 hours times 3,600 seconds per hour. Excuse me. How many joules of energy is that? Well, 60 times 30 times 24 times 3,600. Again, that. I'll go 1.56 times 10 to the 1. Oh, you know what? I'll write out the whole thing. 1, 3 5s, a 2, and 4 zeros. 1, 3 5s, a 2, and 4 zeros, was it, Mr. Duke? Joules. Yeah, 155 million joules. This is why we don't give your parents, or you will never receive energy bill in joules, because that's one light bulb. If we want to repeat that in kilowatt hours, we would write down what they gave me, 155,520,000 joules. I want joules to cancel. I want kilowatt hours, and 1 kilowatt hour is 3.6 times 10 to the 6th joules. you get a much nicer number, 43.2 kilowatt hours. Kilowatt hours. And this is what brings us to a problem, because we've left this bulb on 24/7 for an entire month. Surely, Mr. Dewick, that's going to cost us a lot of money, right? Well, if BC Hydro charges about 6 cents per kilowatt hour, it's going to be 43.2 kilowatt hours times 0.066 cents, but in dollars. It's going to cost you about $2.59, which unfortunately is too cheap, because it's too easy for you to rationalize, oh, that's like half a cup of coffee at Starbucks, I'll just leave it on. And so the message I have for you is, why do we ask you to turn lights off? It's really not to save money, although that does add up. If you do that every day, all year long, that will add up. But it's not going to add up to like $5,000 or $6,000. It's going to add up to a couple of $100 at the end of the year. We're asking you to turn your lights off because we have a finite amount of ability to generate this energy for cheap. And we don't want to have to build more things to generate more energy. Conserve energy so that there's enough to go around. I mean, it's a nice problem to have that we have, and especially here in BC, where do we get our power from? Typically, mostly, almost totally, hydro, which after you've built the dams is pretty green. When you're building the dams, unfortunately, you're flooding back areas, and a lot of those trees then rot and end up in the carbon cycle and all. But once you've done that, it's relatively green compared to other sources of power. But you got to have mountains and rivers to do that. Oh, and you also have to be willing to decimate your salmon runs, because in hindsight, oops, we didn't know that. Am I going to finish? I am. Good. That was very efficient of me. Efficiency. Efficiency is defined as the ratio of energy or power, output to energy or power, input. You know what? I always told you efficiency was the bigger number divided by the smaller. No, the smaller number divided by the bigger number. Efficiency is smaller number divided by the bigger number, but make sure you match units. Don't divide joules by watts. Oh, and then if you want to make it a percentage, times 100%. Why do I remember it that way? Because, Robbie, I know the universe that we live in can't be more than 100% efficient. So if the smaller number is on top, you're good. If you have a bigger number on top, if you're trying to tell me that your object is 130% efficient, you're wrong. Or you'll have won a Nobel Prize in a couple of years. So example 6, let's put it all together. A 60-watt light bulb is connected with 120 volts, alternating current. It produces 58 joules of heat and light every second. It's left on for 8 hours. Electricity costs 6 cents per kilowatt hour. A says, find the current through the bulb. Huh? Well, I'll do that. And really, I'm thinking V equals I times R, and I'm thinking power equals V times I. Those are my big two equations for this unit. Sam, did they tell me how many watts this light bulb is using? Did they tell me how much power this light bulb takes?
Yeah.
How much?
120 volts.
That's the voltage. How much power does this light bulb take? Power is measured in watt? Power is measured in watt?
60,
Yeah, because power is measured in watt? Watts. Yeah, you got the dumb joke? Okay. So this bulb is using 60 watts of power. The voltage flowing through it is 120 volts. So I guess the current is going to be power divided by the voltage. It's going to be 60 divided by 120. I don't need a calculator, Rebecca. It's 0.5. Right? Right. I'll go to 2 sig figs. I'll go 0.50. That's how many amps are flowing through it. That's enough to give you a pretty good shock if you were to touch it. Find the resistance of the bulb. I guess I'm going to use R equals V over I. I used V equals I times R, and I got the R by itself in my head. Looks like we're losing 120 volts going through here, divided by 0.5. Dividing by 0.5 is the same as multiplying by 2. How many? Yeah, typically light bulbs have a couple of hundred ohms of resistance, the incandescent ones. Efficiency of the bulb. So the symbol for efficiency was that Greek letter eta. Well, how many watts are going in? The bigger number. That's going to be on the bottom. How many watts are coming out? Well, ready? How many joules are being used, Duncan? 58 joules every what? Oh, you know what? 58 joules per second. A joule per second, that was the definition of a watt. So even though they didn't say 58 watts, because it's joules per second, that is watts. And so I can put watts divided by watts. I am matching the units. And then I'll multiply by 100 to get it to a percent. And I get this light bulb is about 97% efficient, 96.7%. Wait a minute, Mr. Dewick, what? I've heard that those incandescent bulbs were terribly inefficient. Have I done my light bulb rant with you yet? I did. Right? Well, they're not inefficient if you include the heat, which typically doesn't go to waste. They're actually pretty good if you include the heat. How much energy is being used? Well, energy is power times time. Sam, how many watts of power was this bulb using?
60.
For how long?
8 hours.
So that's going to be 8 times, I think, 3,600 to convert it to seconds, yeah? 60 times 8 times 3,600. You can use a calculator for this one. And I get 1.728 times 10 to the 6th. 1.7 million joules of energy. That's one bulb for 8 hours. Again, this is why, Kayla, we don't give you your energy bill in joules, because you'd freak out. 5.6 billion? What? And that's just a number that people aren't comfortable doing math with either. We convert it to kilowatt hours. I think that's what E would have said, yes? Does E say convert to kilowatt hours? No?
Cost of energy.
Huh?
Cost of the energy used.
Oh, you know what? Let's convert this to kilowatt hours here. So this is going to be in kilowatt hours. We're going to go, we want joules to cancel. We want kilowatt hours on the top. What did I say? 1 kilowatt hour was 3.6 times 10 to the 6th joules. You don't need to memorize the conversion factor. If I ask you on a test or a quiz to convert something to kilowatt hours, I will give you the 1 kilowatt hour is 3.6 times 10 to the 6th joules. .48 kilowatt hours. And now I can calculate the cost. It's going to be 0.48 kilowatt hours times, how much is it per kilowatt hour? Really? Yeah. Again, we make electricity too cheap. It's going to cost you about 3 cents to run this thing for 8 hours. So why do we turn lights off? For the world, not for our wallet. Okay. What's your homework from here? You can try number 1. Number 2 is good. 3 is good. 5 is good. 7, not 6, 7, because I want to cook a hot dog. And we'll pause with that. So there's some stuff. Okay.